The dance of the helix. Unveiling the hidden laws of fluid motion. Imagine a fluid trapped within a transparent cylinder. Instead of sitting still, this fluid is alive with motion, performing a complex choreography where every particle follows a precise, screw-like path. This derivation sheet explores the physics of this helical flow and how we can predict its behavior without ever looking inside the container. The balanced flow. A perfect helix. At the heart of our first demonstration is a fluid that both swirls and rises. Imagine the fluid particles as tiny red dots moving in a circular motion around a central axis while being pushed steadily upward. The result is a helical trajectory, much like the threads of a screw. In this scenario, the fluid is incompressible. This means that as the particles rise and rotate, the spacing between them remains perfectly constant. When we look at the cylinder as a whole, we see a perfect balance. The amount of fluid entering through the bottom disc is exactly equal to the amount exiting through the top disc. Because the fluid is swirling parallel to the cylinder's walls, no fluid ever pushes out through the sides. Because what goes in must come out, the net flux, or total movement of mass across the entire closed surface, is exactly zero. When the balance breaks, sources and sinks. But what happens if we change the rules? In our next demonstration, we introduce a source. Now, as the particles spiral upward, they are also pushed outward from the center. Visually, the helix expands like a growing fountain. This change has a profound physical effect. Because fluid is now being created or pushed out from the central axis, there is more fluid leaving the cylinder's surface than entering it. This illustrates a fundamental principle. The divergence of the flow acts as a bridge between what is happening locally, expansion, and what is happening at the boundaries, net outward flow. We can also see this through the lens of density. Imagine the particles are color-coded, bright yellow for high density and fading to purple as they thin out. In our source demo, as the fluid expands into a larger volume, the particles thin out and fade, representing a drop in density. Conversely, if we create a sink, where fluid is sucked toward the center, the particles crowd together and brighten, showing that the fluid is becoming more concentrated. The spinning paddle wheel. Understanding rotation. Even when a fluid isn't expanding or thinning, it can still have a hidden spin, called vorticity. To visualize this, imagine dropping a tiny paddle wheel into the swirling fluid. In our original helical flow, the fluid moves like a rigid body, much like a solid record spinning on a turntable or a carousel. If you placed a paddle wheel here, it would spin on its own axis while it orbits the center. This indicates that the fluid has a true local spin. Contrast this with an irrotational vortex, which mimics the flow of water down a bathtub drain. Here, the particles still move in circles, but the fluid closer to the center moves much faster than the fluid further out. If you dropped a paddle wheel into this flow, it would orbit the drain, but it would not spin on its own axis. The faster inner current pushes against the paddle in a way that perfectly cancels out the rotation of the circular path, keeping the wheel pointing in the same direction the entire time. By watching these demos, the expanding helices, the fading densities, and the spinning paddle wheels, we gain a holistic view of how simple local motions define the essential properties of a fluid: its expansion, its conservation of mass, and its rotation.